Okay, so let's start. We had a long break, or at least some of us had a long break. So I'm sure the first question that all of you have in mind is this one. So these are the results of the midterms. Hopefully all of you have seen it. This is short 2 exams that are not included in the statistics. But basically, that's that we had. We're going to release the solutions tomorrow, and you can come and look at it in the recitations this week. To give you a little bit more statistics, so I split it here to grads and undergrads. Looks about the same, modulo a little bit of detail, and this is the overall. With 2 exceptions, so it cut off the one below 10 and one above 90. But basically, that's the statistics. And actually, from my perspective, it looks good. I mean, maybe it would be better if it shifted a little bit up by 10 points, but actually, it's a good spread. I mean, I probably said it already. It's bad for the students if the exams are too easy. It's bad for the students if the exams are too hard, because then everyone kind of clamps together in one area, and whether you get a good grade or a bad grade is just a matter of luck. This way, I think it's a little bit better. So to answer the main question that you probably have, so the class is curved. We're taking this into account, we're taking the homework into account, we're taking the projects if you're doing a project. And overall, my current estimation is that B plus is going to be somewhere here. So at least a third to a little bit more than a third will get some kind of an A, and half, maybe a little bit more, will get B plus or something like that. So if you didn't do well, let's say you are below the mean, you can still do well. I mean, there's still quite a few points in the homework. More than half the grade is still out. 3 homeworks and the final. And if you're doing a project, a lot more than that. So that's it. So questions? No questions. Okay, good. So, so a couple other things. So projects. I'm hoping that you're all working. Please come and talk to me at least once in the next 3 weeks in the office hours to discuss the project. On Wednesday this week, I will not have my office hours, so come today. Next week, I will have my office hours. Now, next Wednesday, we're not supposed to have a class. I would like to have a class because I'm running a little bit behind. So the current plan, although it's not final, is that we can have the class here as usual, even though next Wednesday runs Friday schedule. But we're going to do it here. We're going to tape it. Hopefully, enough of you will be here. I realize that some people are leaving town. Most civilized universities don't teach the Wednesday before Thanksgiving, but here we do, so I'm going to use it. Anyhow, so there will be another class on Wednesday. Homework 2 is out. The grades are out. And again, I think it's pretty good. So the average is more than 88. I think it's pretty nice. Quite a few of you got a perfect score, but even if it's not perfect, but close to it, it's nice. Homework 3 is out. Hopefully, many of you have already started to work on it, and you know that you cannot do the second half yet. Hopefully, by the end of this week, you'll be able to do the second half also. Questions? Yeah.
When will we get feedback on the project proposals?
I'm hoping that you'll get it this week, but regardless of that, work and come and talk to me. Other questions? Okay, so let's start. So what I want to cover this week is 2 important algorithms. One of them you already know about because you played with it in homework 2. And today, hopefully, we'll understand exactly what it does and why it's interesting. But let's recap first what we've done and use it as a way to motivate, in fact, both what we're doing today and what we're going to do on Wednesday. So we talked about COLT, or computational learning theory, and used it as a way, this was our way of explaining learning. There were no distributional assumptions. The key assumptions we've made is that the training distribution is the same as the test distribution. And with this, we actually managed to see that we can say something about generalization. Essentially, this theory allowed us to impact what I call model selections. We know that the error that we're going to see in the future, which is denoted here as error D, is a function of the error on the training data plus something, and this something depends on the VC dimension of the data and some other complexity parameters. The VC dimension of the hypothesis space, sorry. And one way to think about it is this way. So what you have here is, on the x-axis, is the complexity of the hypothesis space. As we increase the complexity of the hypothesis space, our training error goes down. You should make sure you agree with that. On the other hand, as you increase the complexity of your hypothesis space, you could overfit. So your test error at some point could go up. And what we want is we want to be able to balance these two things. And this gives rise to what I'm drawing here below the x-axis, which is different hypothesis spaces. So the idea is that this theory allows us to choose, to guide the model selection. We want to start with a small set of hypothesis spaces, simple models. If we see that it doesn't work because our training error is way too much, we're going to increase this and work with more expressive hypothesis spaces. If we see that that's too much, we're going to move to this H3 there, and so on. And all the time, we're going to measure also how well we are doing on some other development data set, which, so that we will not increase the test error too much. So that's basically the theory that we've kind of developed. And this is called structural risk minimization, a theory formulated this way by Vapnik. The name is already known to you. This is the V from VC dimension. So just saying it in a slightly different way, this is the theorem that we almost proved. I mean, we completely proved it for the case of training error being 0, and quoted it for the general case. So what is VC dimension? The way we presented it, it's a combinatorial parameter that is associated with the class of functions and basically guides us in work with in the following way. It says, work with simpler class of functions, you're going to generalize better. Now, let's think about linear functions. In the case of linear functions, we know that they have low VC dimension, for example, lower than quadratic functions. And therefore, if we could, we would prefer to work with linear functions than with higher order functions. It turns out that this isn't subtle enough. And what we're going to do today is we're going to refine it a little bit to depend on the data set. And this exactly is going to give us an algorithmic approach of how to choose good hypothesis. So again, so the way we discussed it is in the context of a fixed class of functions. But in fact, we can parameterize classes of functions in interesting ways. For example, let's think about the class of all linear functions parameterized by the margin. What does it mean parameterized by the margin? It already depends on the data, right? Because the data that I see defines the margin. So I could say, let's consider all those linear separators that separate my data with margin 0.1, or those linear separators that separate it with margin 0.5, and so on. And each one of them is a class of functions, right? So that's what I mean when I say I'm parameterizing the class of linear separators by their margin. Let's look at this example. So we have a data set. Notice that on the two sides of the screen, it's the same data, positive examples and negative examples. So the blue are positive, the red are negative. And I'm proposing here two possible hypotheses, H1 and H2. And I think you would all agree that one of them is going to generalize better. Which one? H2. Why would H2 generalize better? It has a better margin under some intuitive definition of margin. But in terms of VC dimension, the existing theory that we have doesn't help us, right? Because basically, here is what we have, right? So we have here, the training error is 0 in both cases, H1 and H2, right? Both of them separate the data completely. Both of them are taken from the linear class of linear separators in the plane, so the VC dimension of them is 3. And we don't have a tool to explain the intuition that H2 should give better results. So we need to refine this theory a little bit. And the way we're going to do it is we're going to do it by actually defining, defining or refining the notion of VC dimension so that it takes into account the specific data that we have and the margin within which it separates the data. So let's first start by defining the margin in a slightly better way. So the margin gamma I of a point xi with respect to a linear classifier, the linear classifier is wx plus b, is defined as the distance of xy from the hyperplane wx plus b equals 0. Notice that this is wx plus b equals 0 is a set of points, right? All those points x that satisfy wx plus b equals 0. And this was part of homework 0. And hopefully most of you that have seen linear algebra have seen it there. The distance of a point xi from the hyperplane wx plus b equals 0 is given here. It's wx plus b divided by the size of w, absolute value. Okay? If you're not confident about it, go back to homework 0. Try to do it on the plane. I'm going to give later an example. Make sure that you agree with this and you internalize the fact that this is the distance. So this is for one point, xi. If I have a set of points, then the margin of the set of points with respect to the hyperplane is the margin of the point that is closest to the hyperplane. So the same computation as before, wx plus b divided by the size of w, and I'm going to take mean over I, over all the points in the set. So now I have a notion of a margin. Why is this important? Because this allows me now to refine the notion of VC dimension in the following way. I'm going to call H with subscript gamma to be the space of all linear classifiers that separate the training data with margin at least gamma. So this is what I said before. I can parameterize the set of all linear classifiers by the margin. So I have a data set. I fix the data set. For this fixed data set, now I can parameterize the set of all linear classifiers according to the margin. And the interesting thing is that now I have a set of functions. There is a notion, well-defined notion of the VC dimension of this set of functions, or if you want, the expressivity of this set of functions. And it turns out that this expressivity is the minimum between r squared over gamma squared and n plus 1. So let's just see. First of all, you've seen this expression before. Where have you seen this before? This was the minimum, or just the r squared over gamma squared was the mistake bound of perceptron. Magically, it comes back here, the same constant. So what does this tell us? Forget the r squared, which is just an uninteresting constant here, basically just the ball that contains all the points in the data set. What we care about is that the expressivity of the class is inversely proportional to gamma, or to gamma squared. Okay? So basically that means the larger the margin, the smaller the data set, the function class, right? Again, so if you have large margin, 1 over gamma squared is going to become small and small. It means that there are less functions that can do it. Make sense? So if you look at this, basically what I'm saying is, if you care about separating the data with a tiny margin, there are many functions that can do it. If I want to separate it with a large margin, less function can do it. Make sense? So that's intuitively, hopefully it does make sense. You know, just try to fit a thick separator into this gap, and you'll see that there are many options if it's very thin, less option if it's thick. And this is quantified here. So it's a theorem that says, and quantifies it in terms of VC dimension. So therefore, we can just take the theorem that we had last time about the gap between the training error and the true error, and say that this depends on the margin. So the gap between the true error, error of h, and what we've seen in the training data, error subscript tr of h, now is inversely proportional to the margin. We're talking here about linear functions. Okay, so that's, yes?
What is n in that equation?
So n is the dimensionality. So if it so happened that gamma is very large, then r squared over gamma squared is going to be, is very small, gamma is very small, then this fraction is going to be very large, and I'm going to care only about the dimensionality, n. So this is what we knew before, right? We knew before that the VC dimension of linear separator in dimensionality n is n plus 1. We did it in the plane. We showed that it's 3. And in n dimensions, it's n plus 1. Yeah.
What is m? Is that the sum?
M is the number of examples. So that's the stuff that we had before, right? So we always had this component that, you know, because of the pack theory, you care about the delta and you care about the number of examples. And this gap between the training error and the true error is going to be inversely proportional in M. You see more examples, this gap is going to go down. Okay, other questions? Okay, so now we have an intuitive explanation for why we preferred H2 over H1, and this is a key important step toward an algorithmic theory. So what is this observation that we've made? When we consider the class of linear functions that separate the data set with margin gamma, we see that large margin means small VC dimension. Other words, large margin means less expressive hypothesis space. which means that's what we want to be. We want to be able to use large margins so that we are dealing with less expressive hypothesis spaces, and we have better chances of generalization. So the goal is to find a separating plane W that maximizes the margin of a set of examples. Okay, so that makes sense? So essentially, again, if you're looking at this picture, before, we had algorithms that couldn't find these H's, right? So we had perceptron. You give it this data, it would find an H. You had stochastic gradient descent with respect to, choose your favorite loss function. And you knew that if the data is separable, it's going to find the separator, right? But you could not dictate to perceptron or to any stochastic gradient descent algorithm which of H1 or H2, for example, to choose. Everyone is with me? You could find H, but you didn't control whether it's going to be a good one or a not so good one. So that's where we are now. So we made this observation that among all the H's, or the W's, we want to find one that separates by maximizing the margin. And the question is, how do we do this algorithmically? Okay, so again, this is the picture that you want to keep in mind, and you want to convince yourself that you know how to find a separating hyperplane, but at this point, all the algorithmic tools that we developed do not allow us to control which of the H's is going to come out in the output. So the second observation that is going to drive the algorithmic approach is going to be that if we want to get large margin, we should find W's with small size. More specifically, from among all those W's that separate the data, we're going to find the one that has the minimal size. So these are two distinct observations. One of them that we will not be able to prove says something about expressivity. It says try to achieve the largest margin. The second one says if you want to achieve the largest margin, algorithmically, the way to do it is to minimize the size of W. Yeah?
So I thought we said before that scaling W doesn't actually impact.
Excellent, excellent. So that's a great point. So what am I talking about here? I mean, I'm talking about minimal size W, but we know, as Daniel says, that I can take my W, divide it by 7 or multiply it by 7, and it doesn't change whether I separate it or not, right? So there is some subtlety here, and we need to better understand the relation between W and the margin. So far, I just waved my hand here, and I said, we will show that small W is going to lead to large margin, and then Daniel says, something is wrong here, and I agree, something is wrong here. We have to be a little bit more subtle, and let's try to be more subtle in the next few slides. Okay, going back to this picture, this hypothesis, W, B, has many names, right? The same line, I can call it W, B, I can call it 7W, 7B. Everything is the same. Now notice that deliberately I'm going to sometimes use the B and sometimes will not use the B. Sometimes it's useful to have the B, and you'll see in a few minutes why, and sometimes it's better not to have the B, but it shouldn't bother you. So the B, if you don't see it, it's just the n+1 dimensions of the W, okay? We just transformed it in. But So what I'm saying here is independent of whether we carry the B or we don't carry the B explicitly. But you all agree that every hypothesis has many names. But the distance of a point, look up there, hopefully you can see it. This is just a repeat of what I said a few slides ago, and also a repeat of homework 0. The distance is a well-defined thing. You have a point X, you have the W, comma B. Doesn't matter what name you give it. The distance is a physical geometric distance, and it's always computed this way, and that's why we normalize with the size of W. So the intuition is that when we talk about margin, we should care about the real distance, not necessarily just the dot product. Because the dot product, whether it's greater or 0 or not, you can multiply it by 7, nothing changes in terms of the separation. So that's what we have to keep in mind. So we have to really define the notion of max margin in a more careful way. And here is how I'm doing it. So for a set S, max margin is going to be, and let's read it right to left. First of all, I'm computing the dot product, y, wx, size of it, and I'm taking the minimum over all my data set. So I'm finding the data point, the xy point, that minimizes this distance. Okay, this is 1. For a given w, find the closest point. Once I have this, I have many w's that could have done it, right? So if one w does it, for the same distance, 2w is going to do it, 3w is going to do it, 4w is going to do it. So there is an equivalence classes of w's that actually behave the same from my perspective. I'm going to fix one element in this equivalence class. Which one? I'm going to choose the one that has size 1. And I'm going to find the point that gives the maximal margin value across all w's of size 1. Okay, so basically I choose one representative for each w. Notice that, again, I'm reading it right to left. First of all, I do the minimum. I find the closest points. And then I'm going over all the w's, and I'm finding which of the closest is the farthest as the maximum value. Okay, so it's max over w's of minimal distances. Yes?
I understand this, but like in the previous slide, didn't you say that we want a small w? So in this normalized version of w?
Yeah. So we'll get there. We'll get there. So I'm now defining maximal margin. And all I'm saying is that when you define maximal margin, you have to worry about the fact that multiplying something by a constant doesn't change a thing, right? So we have to define it carefully. So we'll get in a second to the size of w. Okay, so the question is, of course, how does this help us to find these h's, right? So we care about the algorithmic questions. So let's look at the gamma, the definition of gamma. The definition of gamma, the output here is a distance, right? It's a number. And I care about the 1h that is doing the best, right? That maximizes the margin. So I can do argmax. The difference between the definition at the top and the one at the bottom is that I added the arg. So I'm asking which w is the argmax of the equation at the top, which w is the one that gives me the max over min distance. Okay? So that's important because, so that's the first interpretation of what I want to do. I want to find among all the W's, choose the one that maximizes the margin. Okay? So remember that I gave two observations, which I'm going to recap now. Keep in mind this interpretation one. Among all the W's, choose the one that maximizes the margin. So that corresponds to the first part of what we said before. I'm going back to the theory. The theory says what you want to do is you want to, because of VC dimension considerations, you want to find a linear separator that maximizes the margin, right? Because the VC dimension is inversely proportional to the margin. So our interpretation one from the previous slides directly correspond to this. Now, the second observation that we want to get to now is, this is actually hard to do just as is. The way we're going to do it is we're going to show that finding small w's is going to lead to a large margin. So the algorithm eventually is going to be, from among all those w that agree with the data, find the one with a minimal size w. So far I gave you just one interpretation that isn't actionable as is. We want to move to the second one. So I'm just that there won't be confusion, I'm not proving the first one. You have to believe it, that large margins are good for you. Intuitively, I assume you get it, but I did not show and will not show the connection to VC dimension. But what I will show is that these two interpretations, the fact that I want to find a large margin, and the way to do it is by minimizing W, that's something that we're going to argue. So let's think a little bit about how do we get from margin to size of W. So we want to choose the hyperplane that achieves the largest margin. That's our goal. We agreed on that. And I'm just rewriting what I've written before. That is given data set. I want to find this W star. The W star that is the argmax over all W's of the minimal distance of X from W. And it's okay for me to just search among all W's that have size 1. And the reason is, as we said, that this is just renaming. The distance is the same distance. Okay, so again, the way you want to read it is right to left. Now, how are we going to do it? How can we find this W? So my claim is going to be that we can solve the following optimization problem in order to find W star. W0 is going to be the solution of the following optimization problem. Let's look at it. I'm considering the set of all xy's such that y wx is greater or equal to 1. And I'm doing argmin on all the w's that satisfy it. So let's just read this. So first of all, we are playing here the game of separable data set. So I'm assuming that S is separable. So what does it mean when I'm telling you, let's consider the set of all w's such that for all x, y, and s, y, w, t, x is greater or equal to 1? Is it empty? Are there w's in this set at all? So the question is there a W? Yes?
I think there would have to be if the data is separable because
Exactly. So let's just say this again. So I told you the data is linearly separable. So there is a W, maybe many W's, such that y W2x is positive. I have a finite data set, so let's take the smallest one. Let's say it's 0.15. So there is a W such that for all x, y, and s, y WTX is greater than 0.15. But if there is W like this, there is also a W such that it's greater or equal than 1. I just multiply it by some constant so that it will become greater than or equal to 1. Okay? So basically, this right side says, because I told you that the data is linearly separable, there are W's here. Okay? Now, among all these W's, I'm going to look at the size of W, the square of the size, and I'm going to choose the smallest one, the argmin. Yes?
Is 1 the margin?
1 is just a number. I could have chosen 7. I could have chosen 0.15. It's just a number. And for every number that I put there that is positive, it's true and it's equivalent. Just because if there is a W, if I consider the set of all W's such that this is greater than equal to 1, the same set of W's, I can take it, multiply by 7, and now they're going to be greater or equal than 7. Right? So I just have to fix something, because, as I said, every separator has many names, and I want to choose one name of all the names a separator has. And that's one way for doing it. Okay? So again, if W separates the data, and the way you are writing it, the inequality, on the right side of the inequality you have 0.15, in the same equivalence class, just by multiplying the W by something, there is also someone that separates it and satisfies greater or equal to 1. You agree with that?
Aren't you just minimizing that top, like that main statement on the top? Wouldn't that just be 1?
No, forget the top for a second. Let's just look at this claim. I'm defining an optimization problem. The optimization problem is take all the W's that satisfy this, and among all these W's, find the one that has the smallest side. That's well defined, and we know that because I told you that the data is separable, that there are W's there. Okay? Everyone agrees with the definition of this optimization problem? So we discussed this set, we discussed taking the minimum, and then the claim is that this W0, when you normalize it, when I normalize it, which means I'm dividing it by its size, now it's going to have size 1. Before I did not know what's going to be. When I look at it here and I compute the argmin, I don't know what the size of W is. Now I know that W0 divided by norm of W, the right side of this is size 1, and I'm arguing that this is actually the same as the W star that I defined above. Okay, so let's say it again. What did I define above? I define our goal, which is I want to choose a hyperplane that achieves the largest margin. This is this W, the one that achieves the largest margin. Now I'm going to argue that the way to do it is to solve this optimization problem, which is among all W's that separate the data, find the minimal size. Okay, so That's my second interpretation. So 2 slides ago, slide 13, I defined the first interpretation. What I want to do is find the maximal margin, W. The W that gives me the maximal margin. Now, this is another interpretation. Among all W's that separate the data with margin 1, choose the one with minimal size. I'm going to argue that these two are equivalent, and the second interpretation actually gives me a direct algorithm. Okay, so first of all, I want to make sure that we understand what I'm saying. Questions? Yeah. Okay, so we said this. We said VC theory, the theorem, tells us that's what you want to do. You want to be able to choose the hyperplane that achieves the largest margin. And it's defined here. Okay? That's what I call interpretation 1. Now I'm making a claim. The claim is that if I'm solving this optimization problem, what is this optimization problem? It says, among all W's that separate the data with margin 1, find the minimal size one. Find the W that has the smallest size. The solution gives you the W star from above. So the solution for this optimization problem is the one that we wanted to find at the top. Yes?
So that, like, standardization, margin, like, that doesn't matter. It doesn't matter what integer that is, just as long as
Say it again, I'm not sure.
like for greater than or equal to 1, like it could be any number.
Could be any number, but I have to fix it. Yeah. So I could have said here, among all W's that separate the data with margin 1, I wrote, I could have said among all W's that separate the data with margin 13, same thing. But I have to fix a number because what I want is I want one element in the equivalence class of all the W's that really are the same. They look geometrically the same, but they have different names. Okay, so that's the only reason I fix it at 1 here. Okay, so basically, I gave 2 interpretations, one that came directly from the theory, another one that is going to give us the algorithm, and I want to argue that these 2 are the same. So let's just go over it. The next slide is going to show that these 2 are equivalents, but really the important thing is for you to understand that these are 2 interpretations of what support vector machines, which is what we're going to call the algorithm, is doing. One, it's the hyperplane that achieves the largest margin among all separating hyperplane. 2, among all W that separate the data, with margin 1, it's the one that has the minimal size. These 2 things are equivalent statements. Why are they equivalent statements? So we can basically do a little bit of algebra and show this. So again, I'm stating the claim here. Let's make sure that we understand the claim. Basically, I'm saying that the normalization of this W0 is the largest margin separating hyperplane. Why is that? Let's define, I'm going to call this normalized W0 W prime. A question? Yes?
In the end, where this going, it's like the W naught, it's a unit vector. You get like 1 over, like when you do 1 over the L2 norm of W, that is the distance. So the smaller the norm, then the larger the margin. Is that?
That's exactly what we're going to see in a second. Right, so let's just wait with this comment. Say it again in a slide or 2. So that's the claim. The claim here is that if you find the smallest W, W0 and normalize it, what you get is the W that has the largest margin. Why is that true? So I'm going to denote by W prime the normalized W0. W star is the one that we defined before, the largest margin separating hyperplane that has size 1. And again, we said that when we did the maximization in the definition, I could also say, consider all W's that have size 7 instead of consider all W's that have size 1. I just want a unique name for a W. So what I want to show is the W prime is exactly W star. So first of all, note that if I take W star and divide it by the margin of the set, then I get something that satisfies the constraint in the top equation there, the 2 stars equation. Why? Because basically W star separates the data. If I divide it by the margin, then Y W star dot product X is greater or equal than 1. Before it was greater or equal than gamma, now it's greater or equal than 1. So therefore, I can say that the size of W naught is less than the size of W divided by gamma star, because W naught was the best one in this set. And W star divided by gamma is in the set. Therefore, the size of W0 is less than the size of W star divided by gamma. And just by the definition of W star, it's equal to 1 over gamma. Okay, so this just came from the definition of W0 being the best element in this set that I defined at the top. Now, I know that for all x, all points in S, I'm going to compute y W prime dot product x. What is it? Let's just substitute. What is W prime? It's W0 divided by the size of W0. So I'm going to substitute here, this is this equality. I'm going to substitute for W prime this guy. So it's W0 here divided by the size of W0. So all I did here is just the definition of W prime. And I'm claiming that this is larger than 1 over this size because I know that this is greater than 1 just by the definition of W0. So it's greater than 1 over the size of W0. And from here, this is just greater than gamma. So what did I show here? Basically, I show that W star has larger, the size of Y W star X is greater than the margin. Now the size of W star, W prime is 1. By definition, again, by the beginning of the proof here. And therefore, W prime is the largest, corresponds to the largest margin, therefore it's exactly W star. Again, let's say this, the final thing again. What we showed, we know that W prime has size 1. If we remember how we define W star, it's the one that has the largest margin among all those that have size 1. And therefore, W star is exactly W prime. So what have we shown? And I think you should, you want to look at it again and convince yourself. Basically, the important thing for me is that you'll understand these two different definitions. You'll understand that if you want to maximize the margin, the way to do it is to consider all the separating hyperplane and take the smallest W. When I'm defining all the separating hyperplane as all the separating hyperplane with margin 1. Okay, so let's take a few examples. So here is one way to think about what we're doing here. So what is it that we see here? So I'm drawing, let's look at the, well, doesn't matter, the H2 one. So you see the separating plane in the middle. This is WTX plus B equals 0. The one on the left is WTX plus B equal minus 1. The one on the right is W2X plus B equal 1. So both of these neighboring hyperplanes are those that satisfy WX plus B equal absolute value equal 1. The same thing you can look at on the left side, right? So if WXI plus B is greater than 1, then the points are to the right, they're positive examples. If it's less than minus 1, they're to the left, negative examples. So that's basically what we're doing here, right? So we normalized the W so that the points that are closest, those that I circled, are lying exactly on the WX plus B equal 1 or minus 1. And you can always do this, right? So in your original way you've written the W, you had some value when you did a dot product WX plus B. You could have had 0.15 or you could have had 7. And you can normalize and change the size so that these points now become equal to 1 and equal to minus 1. So the assumption that we are working after, this is, I'm just repeating what we've said before to make sure we understand what's happening. The data is linearly separable. So if I take a points, in this case x0, comma y0, and I'm assuming that it's a 1 that satisfies wx plus b equal 1, then its distance from the hyperplane, again, using the same formula that we talked about before, what is the distance of x naught, y naught from the hyperplane w? From the hyperplane x plus b, wx plus b equals 0, it's just this distance, right? So it's, okay, the bottom part of the yellow rectangle, it's wx0 plus b divided by the size of w, which happens to be just 1 over the size of w. Okay, so the distance of the points that are just on the separating hyperplane, those points that I circled, from the hyperplane is exactly 1 over w. And therefore, I want to maximize this, right? I want them to be, the closest points, I want to be farther away, which means I want to maximize 1 over w, or I want to minimize w. That's basically what we did, just summarizing. The distance, now I'm writing it slightly differently. Before, on the left side, I just took 1 point and said its distance from the hyperplane is 1 over w. Now I'm taking 2 points, a blue point that is on the line and a red point that is on the line. The distance between them is 2 over the size of w. Okay? So essentially, I chose this line to be exactly in the middle. If I move it a little bit to the left, I'm not doing my best toward one of the sizes. So I want to be exactly in the middle, so both the positive examples and the negative example, the closest one of those have the same distance, which is 1 over w, so the distance between them is 2 over w. So again, what have we done? We looked at all possible w's. You know, you can do this with many, many w's. I scale w so that the constraint is tight. That is, that the extreme points, the closest points, are like this, right? So they satisfy minus 1 if they're on this side, and plus 1 if they're on this side. And then I chose the W that has the largest margin on minimal size. Okay, so here is homework for you. I'm going to spend a little bit of time on it. So what I did here is I did something that I want you to do at home. Let's see. I don't know if you can read it completely now, but you'll be able to read it when you work at home. So here is a two-dimensional example. I have 4 points here. These 2 points, -1, 1, and 0, 0, they are both negative examples, these two. And then two positive examples, 1, 1, and 2, 0. Can you read it? Okay, so you have these 4 points. Now, once you have these 4 points, 2 negative here on the left, 2 positive here on the right, you will convince yourself that the best line that separates them is this guy here. Okay? It's 2 dimensions. You should be able to do this and convince yourself that this line is really the line x plus y minus 1 equals 0. Okay? Everyone agrees? If you don't, you'll convince yourself at home. This is the line, right? It goes through the point 1, 0 and 0, 1, and therefore it's the line x plus y minus 1 equals 0. Or, the way we are writing lines or hyperplanes, w is 1, 1, and b is minus 1. Again, you should be able to convince yourself that these two representations are the same. In, I don't know what, 5th grade or 7th grade or something, you called it x plus y minus 1. Now we are calling it w equal y1, b is minus 1. Okay? Same thing. Now, with this, you can now do all the computation that we've done before, right? So you can compute for each point its distance from the hyperplane. I'm doing it here for 1 point. Here is the point, this point, 1, 1. I'm computing its distance here from the hyperplane. And what you will get is, because I know that this is the closest one, so I took the point 1, 1, dot product with 1, 1, minus 1. This is the minus 1 from here. Divided by the size of w, which is square root of 2. What you get is 1 over square root of 2, which is also 1 over size of w. That's what we expected. Just do the math with these points and convince yourself. Now, I could do the same thing with another representation of the same line. So the line x plus y minus 1 equals 0, which I drew there, has many other names. I could call this line 2x plus 2y minus 2 equals 0. Same thing. It looks the same. So I'm doing this here, and I'm taking another line. Now, in our language, w is 2, 2, b is minus 2, and you can do exactly the same thing. And you will find what is the plus plane, sort of the one to the right, on which the positive points lie, and the one on the left will be the minus points. You can take one of the other points, the 0, 0, or the minus 1, 1, and compute the two. Now, notice that when I gave you these 4 points, I gave you this linear function that separates them. Everyone agree that this separates them? But it's not the only one that separates them, right? In fact, there are infinitely many hyperplanes that separate them. I'm giving you another one. This is this vertical line here. Okay, you see? That one that goes through x equal a half. Vertical line that is x equal a half. In our language, do I write it here? Okay, here. Another separating line on the top right corner is w equal 1, 0, b equal negative a half. This is the vertical line x equal a half, or x minus a half equals 0. That's another separating line. what I want you to convince yourself that among these two that I gave you, the x plus y minus 1 equals 0, and x minus a half equals 0, the first one is better. Okay? You should convince yourself that using the consideration that we played with just in the last few minutes, you have tools to convince yourself that the W11 b equal minus 1, this one, the diagonal here, is a better separating hyperplane for these 4 points than this vertical one. Okay? It's the same game that we did, that I showed before with the H1, H2, but now you're going to do it with numbers. So there is a continuation here where I'm actually doing it. We look at the second plane, W equal 1, 0, B equal minus half. Again, check the 4 points. Convince yourself that if you want to maximize the margin, you can do it by minimizing W, and this diagonal is going to be the right choice. Yes?
Left panel.
Yes.
When you say distance from 0, 1 close to the plane, where weight is 1, 1, and then below you have like some operation, where do you include the 0, 1? Where is the 0, 1 multiplying the 1?
No. So here I'm taking this plane, 1, 1, with b equal minus 1, and I'm computing the distance of the point 1, 1 to it. That's what I'm doing here, right?
Oh, okay.
It's it's w times x minus 1 divided by size of w. Okay, so it's 1, 1, dot product with 1, 1, divide minus 1, minus, it's the b, divided by the size of w, which is square root of 2.
Okay, so that when it says distance from 0, 1, that's not then what we're doing? Or is that a
You're talking about here?
No, on the left. Like distance from, like where the
Oh, distance from 1, 1.
Oh, okay, sorry. I thought it's 0, 1.
I hope it's 1, 1. Yeah, it's 1, 1. If you look from a close distance, you'll see it's 1, 1. Yeah. So hopefully it's correct. But anyhow, this is a game that you can all play and convince yourself that all the abstract things that we played with a little bit earlier works on the two-dimensional plane. This is the same thing that you played with when you did plane geometry, basically. Yes?
So it seems like this approach would be very influenced by the points that happen to be close to the classifier. So like you might have a very large data set, you draw your separator with a large margin, but you could get one more point, that point could be noise, but it's very close to that margin, and you might have to suddenly completely adjust it and maybe come up with a worse separator.
Yeah, excellent. So here is the observation. The observation is that the W that I choose, or the separating hyperplane that I choose, is highly influenced by these points that are closest to it. So if I take this data set and I do nothing but adding 1 point, and it's here, say a red point here, it's going to change everything. Yeah. And that's the good thing and the bad thing about this algorithmic approach. It's highly influenced by the closest points. So what we want to do is we want to relax it a little bit so that it doesn't suffer so much from these kind of extreme points or just a little bit of noise. But let's first formulate what we've done so far. So what we've done is we formulated the hard SVM optimization problem. We showed that the sought-after weight vector is the solution of this optimization problem. Minimize the size of W, or half the size of W. Hopefully you would agree it doesn't matter. Just nice to write it this way. Such that this W separates the data with margin 1. Okay, that's what we said, right? So this was the claim that we made, that the guy that we are after, the W we are after, is the one that among all these W's that satisfy y, W dot product x greater or equal to 1, choose the one that has smallest W square. Now, that's the problem. So that's support vector machines, and we'll see in a second why it's support vector machine, although Daniel's comments already says why this is. Now, this is a quadratic optimization problems in n+1 variables, right? Because we have the n variables of the W and the B, or the n+1 variables of W if you already transformed it. And it has a unique solution. I'm just writing it in a slightly different way to do it when we see the picture here. Minimize W transpose W. This is the size of W, subject to these constraints, right? So we have, for each data point, we have a constraint. Each data point has to be separated correctly. It should be placed by the W on the right side, and this is the set of constraints. And the margin of the linear separator, again, we said it before, is 2 over the size of W. Okay, so why do we call it support vector machines? So it's the fact that W star, the chosen W, is supported, really, mathematically, it's the linear span of the examples that are exactly at the distance 1 over size of W from the separating hyperplane. And these are called support vectors. So these points that I circled here that are sitting on the WX, Y WX equal, absolute value equal 1, that is the red ones, or the WX equal 1, the blue one, WX equal -1, these are defining the W. I don't care about all the other points. And that's why they are called the support vectors. So a theorem would say, if W star is the minimizer of this SVM optimization problem, this is W star is the W we care about, let's denote by I the set of all xi's, it should be, that satisfy WT x equal 1, then there is a set of coefficients, alpha i's, positive coefficients, such that W star is defined as the linear sum of all these xi's. So W star is the sum alpha I, yi, xi. Now, this should ring a bell, this representation. Where have you seen this before? Kernel. This is the dual representation. In kernel perceptron, we also showed that W is really a linear sum of all the examples on which I made mistakes. Here, quite similarly, the chosen W is a linear sum of all those examples that matter. All those that are extreme, the closest to the line. So just like before, we can talk about the notion of duality. This is the dual representation of W. And a lot of the algorithms that people are using, in fact, search for W not in the primal space, which is the optimization problem that I defined before, but rather in the dual space, which is the problem that I'm showing here. I will not get to it now. In fact, okay, so I'm going to stop here. What I'm going to do next time is I'm going to spend a few more minutes relaxing the problem. Because as we said, this is too strict, because if I add one more point, I'm changing the W too much, and I don't want to do it. So we're going to relax it a little bit and will not force things to be so strict. And then we're going to move to boosting. Okay, see you on Wednesday. Hi.
I have a question. How do we end up with the 1/2?
The 1/2 doesn't matter. If you minimize this, you minimize it with the 1/2. The
also
reason
wouldn't it be the same, like 1 over W, then 2 over W? Like whatever.
no. So this
Isn't that
really
also the same as well?
no. This is important
Okay.
because I showed that the distance is 1 over W
Yeah.
from the point to the hyperplane, and
want it to be
therefore
on that same, yeah.
from the plus to the minus is 2 over W.
Yeah.
This is unimportant, the half here. This is just because people like to write it this way, so when they do derivative,
Then that
the 2
becomes like just
disappears.
W, because you have it the square, so then you do, okay.
Yeah.
Okay.
This is unimportant.
Okay.
It's just tradition. Sure.
If you want our exam, we can pick it up in your office hours?
No, in the recitations.
Or recitation?
I said it maybe before you stepped in, yeah.
Okay.
Hi.
I actually have a question about neural networks. So just kind of as an exercise, I was trying to write a neural network from scratch, basically.
Backpropagation?
Yeah.
Okay.
And so I was trying to work with the scikit-learn moons data set. And so for some reason, without the softmax at the last layer, it just didn't work at all. So it just, well, it did. It drew a line. But then adding the softmax at the last layer, for some reason, made it work.
But
I'm-
how many layers did you have?
It was 3 layer.
And in the middle you had nonlinearity?
Yeah.
Okay.
And it just, so it was with the sigmoid activation function too, so everything is between 0 and 1.
Yeah.
So I wasn't, like, I don't understand how adding a softmax layer at the end could make that kind of difference.
Okay, so the question is, how did you make the decision? So if you don't have a softmax in the last layer,
You just pick
you
the max.
get, so you had it's a binary classification?
Yeah.
Okay, and you can get any number you want, right, in the output. You can get large numbers in the output, in the dot
Output.
product that you get in the output.
No, that goes through sigmoid also.
No, but you said that you didn't have sigmoid gates
I
in the last layer.
Yeah, I did. 2 output neurons, both with the sigmoid.
Okay, just a second. So you had 2 output neurons. One was
Yeah.
for positive example, one was
Yeah.
for negative
And it
examples.
just picked whichever one.
Okay.
And that just ended up giving a really bad classifier, but then for some reason, when I put an additional softmax on top
each
of
one
that,
of them.
yeah, then for some reason, it started actually giving a decent classifier, and I don't understand how that softmax.
No, something is wrong
Make a
because basically what you said is you have 2 values, A and B. And A, you checked whether A is greater than B, and it wasn't giving you good results.
Yeah.
And then you applied the same function that is monotonically increasing on A and B, and now it gives you the right result. It cannot be
Yeah.
because if the output of this is a monotonically increasing function. So if f of A is greater than f of B, A is greater than B, and vice versa.
Yeah,
So something is wrong here.
I think the only difference it can make is it's affecting the training somehow.
Oh, you're doing it in training, not
Yeah.
in decisions.
Yeah. Because adding softmax on top of it changes how the cost function propagates
Which loss function did you use?
cross entropy.
So now you're saying, so you send this to cross entropy.
It's just, I can understand, like, if it was a tangent evaluation function, that's like a negative equivalence, so, you know, softmax scales it to between 0 and 1, so I can understand how that would make a difference, but sigmoid is already between 0 and 1, so I don't understand how a different function that also sends it to something between 0 and 1 could make a difference. Just for some reason, that softmax made a really big difference. I don't see why.
Just a second. So when you say softmax, what is the function that you applied?
Just, e of x over the sum of x's. E to the x. Something with e to the x. That's after it already goes to the signal.
So x is the output of the signal.
Yes.
Actually, but something is wrong here, right? You shouldn't do that. Because, in fact, if you just take one of the networks, one of the neurons, you train it as a binary classifier, right? You don't need the second one at all.
Right.
What happens if you just look at this one and do greater than half?
I hadn't tried that, but I wanted it to do.
Because what you're doing here is much stronger, right? So essentially what you're telling each neuron is what the other one thinks.
I guess, yeah. If I only had one neuron, I wouldn't necessarily generalize
Why
to
not?
classes.
No, it's binary.
Right, but if it wasn't binary, it wouldn't work.
Okay, so
If I wanted to do multi-class classification, this way I could just add them
This is,
together.
this is the right way to do multi-class classification, but I'm trying to understand what is happening here. And this is the right way to do multi-class classification, basically. The way you did it with the softmax, because essentially you're training jointly with all the labels. But for the binary case, that should not make a difference.
Even with multi-class classification, why isn't it enough to just pick the maximum point?
Okay, so that's actually, okay, the best example to look at here is actually the linear case. I'm not going to talk about, I won't have a chance to talk about it in class, but think about it this way. So think about linear separation, but the same thing can be blown up. So let's assume you have this case. Label 1, label 2, label 3. 4, to make it more interesting, label 4. Now you can see that you cannot linearly separate each class from the others. And when you train, the way you train it is 1 versus all. You say all the 1s are positive for 1 and the rest are negative for 1. All the 2s are positive for 2s and the rest are negative for 2s. So you are basically saying that each class here is linearly separable of the union of all the others, which is not expressive enough. Right?
Okay.
Really what you want to say is you want to say that each class, there is a way to separate one from the union of the other, but it's not necessarily in your hypothesis space.
How does softmax change that?
So the way you did softmax is you basically told in each round to each one of the labels what the others are doing.
Okay.
I can give you a paper to read that actually discusses this.
Okay.
In the context of linear functions, but it's the same thing. It basically does jointly. This is an algorithm that I'm going to talk about. Mention it in the context of SVM. It's called constraint classification. It basically does joint learning on multiple labels. Now, in your data, it shouldn't have done it because the data is separable. So I don't know why it worked. Why it didn't work without it.
Okay.
It could be not enough data or something like this, but basically what you did with the softmax is you gave more expressivity than just the one versus all, right? Because you basically showed each one what the other one thinks.
Okay. I had always wondered what the point of softmax was in general. Because if you use sigmoid anyway, like it always just goes.
So remind me, I'll give you a paper that basically discusses these issues of why it's good to look at the other labels.